Right. Now, the idea here is to use a neural network that can learn to mirror the function of a system. Up until now, we've been using a neural network basically for pattern classification, where the neural network is learning to separate one set of patterns from another. And we have the decision surface, which will separate in the pattern space. And that is a relatively easy concept to take on board and to train. Now, if you want function approximation, the application is considerably harder because we now want all the patterns of the data to fit on the decision surface. And where this has been used, or people have tried to use it, is to monitor complex systems. For example, you could have a manufacturing plant and all the parameters, all the variables. Sometimes the plant is working 100% capacity, others it might be 20% capacity. And we might wish to minimize the energy consumption across all normal operating conditions. And there's clearly a set of parameters that will give you optimum performance. Can we get a neural network to learn those? Another application which has been used, not particularly successful, is to monitor jet aircraft and fighter aircraft, where the speed of decision making has to be so fast the pilot normally can't make the right decisions, and so he or she needs backup. And the question is, can we use a neural network to recognize or to mirror the function for stability? And possibly if Boeing had such a system, we wouldn't have had the problems with the 737 stalling. A bit closer to home, if you have a motor car, you have driving habits. You drive that car in a particular way, whether you're in a 20-mile-an-hour speed limit or if you're going down the motorway. Different parameters, but you have a style of driving. Can we use a neural network to recognize your style of driving so that if somebody stole your car and was doing wheelies and donuts and driving aggressively, the system would recognize it's not your driving habits, and it could be used to close, to stop the car working, to inhibit the car. So lots of interesting problems to consider for function approximation. Right, the key is all patterns of the class must be on the decision surface. Only look at very, very simple problems which are 2 dimensions. But first of all, let's, oops, oh whiteboard, don't mess me about. Oh. I've lost my whiteboard. What is happening to this stupid thing? Hold on, folks. I'll try and get somebody to sort it out. Technical difficulties. Please stand by. Thanks, Jason. I've got the Department Supremo, Dr. Deere, looking at my screen.
Was this the one?
That was the one I was using. Oh,
Just got confused. To make sure they can see it.
Can you see that squiggle? Anybody? Jason, can you see the squiggle? Yes, yeah, good. Right, let's try and continue. Right, where was I? Yes, the training for function approximation. Let's see if I can get slightly thin. That's a little bit too heavy. Let's go down to there. That's a bit better. Right. All patterns need to be on decision surface. So initially, this means output. So training. Initial W. Choose W equals, I don't know, a random vector. Take the first training pattern. And calculate the scalar product W dot I. And let that be equal to scalar value S. Now, if S is 0, and that's going to be very unlikely, do nothing. The pattern, the input pattern I is on the decision surface. It's satisfying the function by the decision surface arising from W. However, if S is not equal to 0, we need to update W. And the update is the same as we used in the original feedback training. W prime, the updated version, is going to be equal to W, the initial weight vector, plus a correction factor times the input pattern. And we need to choose a W so that W prime, the updated weight vector, with the current pattern equals 0. And note that that is 0. With the previous training algorithm for pattern recognition, the updated weight vector with the current pattern had to give a response which was equal but opposite sign to the original weight vector with the input pattern. If W.I was S for the error correcting feedback for pattern recognition, W prime.I had to be equal to minus S. It's not minus S now, it's 0. Now, if I substitute in this equation for my updated weight vector, I get W prime, sorry, W plus Ci, these are vectors, dot I equals 0. Multiplying this out, I've got W dot I plus Ci dot I also equals 0. But we know this was the original weight vector, scalar product with I, which back here is there. We can substitute in this equation S plus Ci dot I equals 0, and this will enable us to get our correction factor C equals minus S divided by I dot I. Very similar to the error correction feedback, but in the error correction feedback it was minus 2S. So the algorithm is very similar, but this time instead of putting the input pattern on the opposite side of the decision surface, it's putting it exactly on the decision surface. And unfortunately, almost every training pattern you put in training will need a correction, because the likelihood of a pattern being on the decision surface is very remote compared to it being on one half or other half of pattern space. Right, now to give you an idea of how this might work, let's take a simple example, and I want to devise a speed monitor. And let's take a speed of 30 miles per hour. Or to keep the numbers reasonable, let's have 1 mile per 2 minutes, which is 30 miles an hour. Right. Let's go for a two-dimensional space, which we can draw. Let's have positive and negative coordinates, and let's have the first dimension distance, and let's have 0, 1, 1, 2, and this is going to be time, which is going to be minutes. And let's again have 1, 2. And we know the don't you dare. We know the training patterns. Are going to be I1 equals 0, 0, because the speed function will go through the origin. No need for any bias, that makes it simpler. And another training pattern would be for I2 at 30 miles an hour or miles per minute, it would be 1 mile in 2 minutes. Right. If I can find a weight vector, which goes through the origin and goes through 1 mile in, 1 mile in 2 minutes, a training pattern would be there and a training pattern would be there. The decision surface that's on those two lines is the line going through them, and the weight vector is going to be somewhere along there, which defines the decision surface. So on the decision surface, it's 30 miles an hour. It would be 4 minutes, 2 miles. It would be somewhere up there. 1 mile in half a minute would be somewhere there. If we are on the plus side of that surface, you are going faster than 30 miles an hour. If you're on the negative side of the surface, you are going less than 30 miles an hour. And that's how the system works. Now, how do we find the weight vector? Well, the training patterns are 0, 0 and 1 minus 2. And the output has to be 0, unlike the previous case where it will be plus or minus depending on the class. And to find a weight vector, well, clearly any weight vector with 0, 0 goes to 0. Every weight vector will go through the origin. So we only need to look at the second input pattern, I2. And by logical reasoning, if I want a scalar product of a W with this pattern to give a 0 output, a suitable weight would be 2 minus 1. Sorry, that's 1, 2. And clearly 0, scalar product there with 2 minus 2, 0. That is a solution. Now, can somebody else name another solution by inspection? Anybody coming on? This would be a case of offering a bag of crisps if we were face to face in the lecture theatre. Come on, another weight vector that will solve the problem for the speed. 4, 2. Yep. 4 minus 2. Now, that seems a pretty trivial thing to do, but it is important because we have, or the system has developed an ability to perform a dynamic function, which is speed, and speed is distance over time, without doing the mathematical analysis. And if you represented this problem in a slightly different way, maybe a toy for a young child, if you had 2 inputs, knobs which you control, you can move them that way and you can move them that way, and you have a box, a door if you like, and when you get to a certain position equivalent to the F equals 0, the door opens, and if you're not in that position, the door remains closed. By randomly tweaking these 2 knobs using Hebbian learning, you can end up with a condition, a weight input, which would be one of those 2, which would open the door. Now, at no point have you any knowledge of dynamics, but you know the input conditions and you know the output condition, and you can end up with a solution. So the system, the dynamic equations have emerged without you doing the analysis. And that is quite a fundamental, the interesting thing. The system is learning without reference to the mathematics. Now, when you go to real problems such as aircraft control, or even car control, you will have a much more complex function. And if I draw a function with a weight vector out there, the function may well be something very strange like that. And this could be the plus side, this could be the minus side, this is the F of 0. And clearly one would need many nonlinear terms for a real problem. But the principle is there. The functionality can be created in the network without you knowing the mathematics. And that is an interesting concept. Okay, folks. Let's just summarize analog nets. I'm now coming to the end of what I want to talk about on analog nets, and this possibly has been the most difficult part of the course. It's the most conceptually difficult part to understand. And what I want you to take from the lectures so far is not the methodology, but an understanding of how they work and when they work, and also more importantly, when they don't work. And so for analog neural networks, the device we're using is the McCulloch and Pitts neuron. often referred to as M and P. It is a system where you have weights which weight the input and they are combined to give an overall output. This same device is sometimes called a linear discriminator. It's a linear discriminator because the single neuron, the decision surface is linear. Some papers call this device a binary pattern classifier. Now, I don't like this title myself because it is confusing. The binary part is confusing. It's not a classifier of binary patterns. It's a binary classifier of patterns, i.e. the decision is a two decision. It's not relating to binary patterns. Not restricted. Right. Minsky and Papert came along in the 1990s and they coined a new name for these devices, which was perceptrons. Again, exactly the same principle, the scalar product of weight vector with inputs. And that, for high-level systems, led us to the MLP, which is the multi-layer perceptron. Yet another group of researchers back in history thought, and they are correct in thinking, that these neuron models can perform logic functions, and they called them threshold logic units. Which is very interesting conceptually, because if a neuron can perform a NAND function, and we know it can in 2 dimensions, it's quite simple to demonstrate that it can. If we can get a NAND function, a neuron performing a NAND function, then any process can be built out of neurons. And so that has an interesting take on how computing could develop. And these are all the same. So if you see these devices, they are all weighted input models. And in exams, I will usually use the word McCulloch and Pitts for the single neuron and MLP for the multi-layer perceptron. Right, so those are the devices. The real problems. The first one, of course, is training. The training is iterative and recursive. We go through the training set to develop a weight vector. If that weight vector changes at any point in the training set, you have to go back and check that the earlier patterns are still correct. And this can lead to very long training sequences. And people will argue that if we have to do computing for an hour, a day, even a week to train a device on a problem, if we converge to a solution, then the testing is very fast. In terms of computing time. Now, if we're thinking of the natural systems and and we are using biology to inspire our technology, Clearly, the humans don't have this training problem, because if I were to show you two random shapes, a face, for example, and that could be Fred, and I give you another face, and that could be, I don't know, Jane. Now, you don't have series of iterations to learn that face. If it was a real picture, you would recognize it immediately, having seen the first one. You are making the input-output link immediately. So in humans, we don't have this long recursive training. So maybe our model is not a good natural model. The other problem we have is the network structure. You have to have a physical structure of a network with adequate nodes in the layers to support the functionality of the problem. And again, we can learn lessons from logic design. If we want to design a logic function, initially from the truth table, you don't know how many AND gates you need on the front layer and how many OR gates, usually one, of course, on the output layer. So if we have a structure that will not support the functionality, it will never train to a converge to a solution. The other problem we have is training. And with the training net size, the number of training patterns must be greater than the dimensionality. And of course, the more training patterns we have, the more difficult the training is going to be, the more likelihood there's going to be an error in the training iteration. And for real problems, we might be talking of hundreds or maybe thousands of training patterns, and the dimensionality can be hundreds of dimensions or even higher. The other problem, beware, mainly because of this training restriction, that the training has got to be greater than the dimensionality, beware of simple tests. They can be misleading. If the dimensionality is, the number of training patterns is less than the dimensionality, it will work. And remember the example I gave you, that if you took 6 lottery numbers, 3 of which were winning tickets and 3 of which were losing tickets, the dimensionality is 6, the number of training patterns is 6, you would be able to separate those out with a neuron. But it's not solving the problem of picking winning lottery tickets. And the other problem, of course, is, what was I thinking about there? Right. Yes. Always test on unseen data. Do not evaluate on training data. Yes, if the training data isn't separated, chances are the system will not work. But if the training data is separated, it doesn't mean you've got a solution in general for the problem. So that is an overview of analog neural networks. So I now want to start thinking about alternative structures and different models for the neuron that doesn't involve this vector model. But before I go there, I want to look at a pattern recognition method, which was, again, its historical interest. It was way back in 1960 it was first proposed. And this gave us some ideas for new models from, amongst other sources, new models for a neuron. So now for something completely new. And the method I want to talk about is known as the Browning and Bled n-tuple. And it was about 1959 it was first published. Browning and Bled, a couple of Americans, that's near there, were interested in pattern recognition, and they were trying to automate. Don't! Right, stay there. They were using this, they were trying to automate character recognition. And their data was 16 by 24-bit images. They had some interesting results. They were able to recognize handwriting individual characters to about 80% success, which is much better than chance. But of course, in the context of, say, a postal code, where there's no redundancy, 80% per character means the chances of getting a 6 or a 7-string character code correct is almost zero. So it was a good idea. It had some interesting properties, but it wasn't commercially viable at the time. So what's it all about? And we're basically matching pixels. In the same way as we are in a distance classifier. If I were to take one pixel and again it's binary, the pixel can either be white or black. That's white, that's black, if you like 0 or 1. So if I was trying to make a decision on a single pixel, the maximum I can have is 2 classes. Now for character recognition and numbers, we need something like 36 classes, and a single pixel will only give us a possibility of 2 decisions. If I now take 2 pixels, the number of classes, I'll write them down in binary. It's going to be 4 values. And the values are going to be 0, 0, 0, 1. No shouting needed because it's not a K-map, 1, 0, and 1, 1. There are 4 values, and there are many ways of grouping these. I can separate them 0, 0 from the rest, which would be 0, 1, 1, 0, 1, 1. And I think there are 3 ways of having 1 from 3. Or I can separate them 2, say 0, 0, whoops. 1, 1 from 0, 1 and 1, 0. And I think you will find that there are 6 ways of having 2 from 2. 3 from 1 would be the same as 1 from 3, and so that gives us 9 different groupings. This means if I'm looking at 2 pixels, I can have a variation of inputs 0, 0 and 1, 1 for the same class. And the other side 1, 0 and 1, 1. Whereas with the 1 pixel, I only had 2 decisions I could make. So if I now go to n pixels, the number of states are going to, or the values, are going to be 2 to the n states. So if I take n equals 8, there is a potential of 1024 values the group of n pixels, which is now referred to as the n tuple. So Browning and Bledsoe's ideas were, we're taking groups of pixels, we can have variations of values within the pixels which can be classified as the same class. So let's have an example. And I'll use 3x3 images for simplicity. And let's take letter T. Letter T. And my 3 reference patterns. Let's start off with a T like that. Let's take that with a T with a shorter center. And let's take a sloping T like that. Now, if they're digitized on 3x3 pixels, we would have an image with a perfect horizontal top and a perfect vertical center for that image. For this one, it would be a shorter vertical. And for the sloping one, digitized, we might end up with an image that looks like this, where the top is sloping, and the best I can do is a slope like that, and the center is like that. So those are the 3 digitized patterns. Now, what Browning and Bledsoe did for each class obtain a list of n-bit states. Right, defining the n-tuple. Ideally, random. Again, looking at biology, the connections of the brain are pretty certainly likely to be random, and Browning and Bledsoe initially chose random samples, but to follow it and to follow what's going on, we will use it's easy to follow. And the linear samples, n is going to be 3, and that is going to lead to samples which are rows of the image. So the T lists. And these are the rows, of course. Going back to my first pattern, the sample of the first pattern T is black, black, black. Let's assume across is 1. In binary in 3 bits, it's going to be 1, 1, 1. Let's call it, for simplicity, in decimal, state 7. For the, don't you disappear. For the second sample, second training pattern, top row, 7 again. We've got 7 already. It's an allowable state in the top row. Nothing needed. We know 7 could occur in the top row. But when we take the third pattern, we've got 1, 1, 0. It is going to be state 6. So we have now 2 possible states in the top row of the T detector. It can be state 7, which is 1, 1, 1. Let's just draw them as crosses. And it can be 6, which is 1, 1, 0. Now for the middle row, 0, 1, 0. Same for the second pattern, but for the third pattern is 0, 1, 1. So we can have states 2 in decimal and 3. And 2 is going to be that, and 3 is going to be that. Right, for the final row, the bottom line, 1, 0, 1. So it's going to be 1, 0, and 1 again, and 1 is going to be, have I got that right? No, 2, 0, 2. And those are the actual intervals as images. So we build up a list of allowable states. Now, if I'd only taken the first pattern, I would have a 7, a 2, and a 2. If I took an unknown pattern, let's take this that looks a little bit like a T with a variable thickness of the top line. It's something like this. If you saw that as we're told it's a character, I think you would say it's the letter T. It clearly, the value of the top line would correlate. It's an allowable state. But the second function is not expected for a T. And the third one, it would only give a score of 2 out of 3. If, however, I look at all the states in comparison, saying sample 1, 2 choices, sample 2, 2 choices, sample 3, 2 choices, and I'm not constraining all the samples to have come from one training pattern. We're just saying in the top row, this is what we can have. In the middle row, this is what we can have. In the bottom row, this is what we can have. We are able to get a maximum correlation of sample 1, sample 2, sample 3 for 2 cases for each sample, 2 to the 3 patterns recognized. Of course, it will be the 3 training patterns plus 5 others. And those 5 others are the generalized patterns, generalization set. So now we can work out the number of patterns recognized. It will be the training set, which was that one. It would be the other training pattern. It would be the third training pattern. But it would also be, if I had 7, 3, 0, that would be recognized, 7, 3, and 0. It could be 7, 2, and 0, 7 allowable, 2 allowable, 0 allowable. It would be 7, 2, and 0. And plus 4 others. 1, 2, 3, 4, 5, plus 3 others. Right. I'll leave you find the other 3 as an exercise yourself. Now, if I were to test on a non-T, and let's take a typical letter X. What is the response I'm going to get from this pattern? Well, top line state is 5. Back to the lists. Where are we? 5, no, 5's not allowed in the top row. The middle state for the X was 2. I think that is allowed, and 5 is not, so we would get a score of 0, 1, 0. The total score would be 1 out of 3, far less than the maximum response of 3 out of 3. So we could put a threshold on the correlation and reject that as not being a T. If I take a pattern L, and I think if my memory serves me right, that would give a 0, that would give a 0, that would give a 0, that would give 0 out of 3. So we are clearly discriminating between T's and X's. Now, this is a very low resolution example to show how it behaves. As I say, the original experiment by Browning and Bled was images which were 16 by 24. Their typical interval size was 8, which I think meant they had 32 samples rather than my 3. The whole thing was written in primitive computer language in the 1950s, and they achieved about 80% on hand-printed single characters, which was in many ways impressive, but in many other ways not good enough for commercial development. And of course, what one would have would be a series of lists. So having got the T list in training, there is the T list. In a real example, there would be maybe 32 samples. We would have 8-bit intervals, so the number of entries in each sample which are allowable could be quite large, and an unknown pattern would compare its samples with the A list, the B list, the C list, right the way through, and the numbers to find the maximum correlation. Maximum correlation, you make a decision. So it was an interesting idea. It's moving away from pixel matching to interval matching, but it wasn't practical at the time, and it really didn't take off in the 1950s. But it is very influential in developing a new model for a neuron, which is based on logic, because clearly what we are doing here is looking for allowable states, and they didn't realize at the time, but this membership, instead of searching a list of entries, can be implemented with a logic function. Because if I call that A, don't move, A, B, and C, nowadays a logic function to recognize membership 6 and 7 would be F equals A, B, C, or A, B, and not C. So a logic function can do the membership detection. They didn't have logic in 1950s. It was still almost in the valve era, but this subsequently led to a new approach to a neuron model. And guess what? The new approach is to use a logic function to represent the function of the neuron. So I want to leave it there. And next week, we will start to look at the digital model of a neuron using logic functions. I've lost the conversation on my other computer, but if anybody has any comments, please feel free to tell me about them. Okay. Anybody still there? Right, let's go to conversations. Right, chat's going on. Sweet, thanks. It's yeah, thank you. N equals 10, 2 to the 10, 20 to the power 10. Big numbers. Somebody says 2 to the power 8. Hang on, have I made a mistake there? Yes, you could be right, Ahmed. An 8 tuple will have 2 to the 8. A 10 tuple will have 2 to the 10. The important thing is, as the number of pixels increases, the space, the variation within that n tuple goes up exponentially. And if I were to take a n tuple of 20, then there would be 1,000,000 different patterns that I could display on 20 bits. And so we can have big sets and big variation within the n tuple, and we can still detect those. And that's the key to the Browning and Bled method that we are going to develop next week. Okay, guys, 11:58. I'm finishing now. Anybody in serious trouble, contact me or email